Super excited to introduce today's main speaker, Ander Rodriguez. Ander is the CTO and co-founder of Zenrows and comes to with over 10 years experience in web crawling and data extraction. So today, we'll be sharing 7 proven strategies that will transform how your team approaches web crawling. I know I'm excited to get started, and let's just jump in. So Ander, moving on to today's agenda, can you give us an idea of what we're going to be covering?
Sure. So, welcome everyone. This is Ander, and thanks Robert for the intro. Today we'll focus on 3 key areas that can transform your web crawling operations. First, we'll look at how to significantly improve your data collection speed. This is essential whether you're crawling hundreds or millions of pages. Then we'll dive into infrastructure cost, because speed isn't helpful if the solution isn't sustainable. And finally, we'll tackle one of the biggest challenges in web crawling: avoiding blocks and maintaining consistent access to your data sources. These 3 areas are deeply interconnected, and throughout the session, I'll show you how addressing them together leads to much better results than tackling them in isolation.
Okay, that is great. And just to confirm for everybody and those along following, we're going to be providing examples and some demonstrations as we go through each of those areas.
Absolutely. I'll be showing real examples using our demo pages, and we'll see exactly how these principles work in practice. We'll also have time, as Robert said, for Q&A at the end to address your specific scenarios.
Okay, perfect. So before we jump into the 7 solutions, why don't we do a little bit of scene setting? Ander, what are some of the biggest challenges that both developers and companies are facing when web crawling today?
Yeah, good one. The biggest issue we see is balancing speed and avoiding detection. When scrapers try to fetch data too quickly, they trigger both mechanisms and get blocked. Another common challenge is concurrency. Many developers don't have experience managing multiple requests efficiently. And there's the issue of proxy management and cost. People pay for them, but often struggle with maintenance and the cost itself.
And and what about scaling from development to production? That seems to be another bottleneck in the process, right?
Yeah, absolutely. Many teams can get a scraper working on the local machine, but when they try to scale it up, everything falls apart. The parsing methods that work for a few pages become inefficient at scale. They waste time processing unnecessary parts of pages like menus, filters, or ads, when they should focus only on the main content. And as web technologies evolve, these problems get worse. Today's sites use JavaScript rendering, infinite scroll, client-side pagination, and many others, which make traditional scrapping methods obsolete.
Oh, wow. So sort of feels like double folded here. So it feels like not only are the barriers to entry getting higher, but also the process is getting more and more complicated as we start looking at scale. Um, okay, so now that we understand the challenges, why don't we jump into our first strategy for solving them? Ander, can you start by explaining parallel processing to the audience?
Sure, let's begin with something that will dramatically improve your crawling speed. Most people start with sequential processing, crawling one page after another. It's simple but inefficient. With parallel processing, we can handle multiple pages simultaneously, reducing total crawling time significantly. Let me demonstrate this with a few practical examples using our own demo site. Imagine that you target an e-commerce category list that has 13 pages, as shown in this image, but you don't know this info beforehand. Instead of doing 13 requests, as a human good, we can perform the first to get the content and then 12 of them in parallel. When crawling 13 pages sequentially, it takes about 13 seconds, let's say. But by processing these pages in parallel, we can get it done in just 2 seconds. That's more than 6 times faster.
Okay, I'm following, but I guess the question that's going through my head is why 2 seconds? Why not 4 seconds or one second? Can you give us a bit more detail on this one?
Yeah, yeah, great. Let's continue with examples. So here These are predictable URLs based on page numbers and total number of items. So getting the first one will let us create all the page URLs programmatically. If the response time average is 1 second, we would go from 13 seconds to 2 seconds. Why? 1 second for the first response, which is the home page or the category page. From there, we extract the total number of pages and generate a list of all the pages, as you see with the red arrow, page 2/2/3, etc. Then we run the rest of the requests, which are 12 pages in parallel.
Yeah, that's super clear, but I would imagine you've seen some issues in the past. What are some of the most common mistakes that teams will make when trying to implement parallel processing?
Yeah, this might be obvious, but always limit the concurrency and the number of requests you can send. You might decide that the infrastructure can handle scaling up and down, and it sure will. But what happens if there's an issue and you start retrying all the requests? Instead of performing 10 requests per second, they start requeuing and you go up to 20, 50, 100, 1000, etc. per second. Apart from an alert system, this behavior should be limited. Another common issue is not handling the rate or concurrency limits in a distributed manner. Let's imagine a script that will run concurrency limit of 10. If you set the limit inside the script, it will only be applied, well, inside each instance of the script, meaning that the moment you deploy and run 10 scripts, let's say one per target, you will have 100 concurrent requests. There will be 10 scripts running 10 each of them. That's obviously above the limit you started with. A common question or concern is how many requests or concurrent requests or rate limits or whatever to use. Sadly, there's no silver bullet. There's no optimal number or strategy that works for all cases, but we can give it a try. Some factors to take into account are the target site, the response time, how big it is, the size, the number of pages, how many requests we want to perform, and super important, what tools do we have? Because some escalate better than others. Our service providers might have some limit on concurrency or rate limit, and also there might be bandwidth limitations. With those numbers, we can run a load test that increases gradually. Depending on the numbers above and our infrastructure, we can start with just a few requests or hundreds, and then keep adjusting. If you feel brave, I bet that you can prepare a script that will adjust the concurrency limit based on speed, latency, and error rate. ChatGPT or equivalent will happily create a quick script in any language for testing this.
Okay, so we've seen how parallel processing can speed things up, but what about modern websites with more dynamic content? And or how would we handle these?
Yeah, this is where many people struggle. The traditional approach is to simulate user behavior, loading the page, waiting for content, clicking buttons, and repeating. It works, but it's slow and fragile. And you might need a headless browser, which will always be slower and more expensive than regular HTTP requests. Instead, we can be smarter. Modern websites load their data from APIs or internal endpoints. If we can identify these data sources, we can access them directly. Let me show you on our demo site how this works in practice. What's interesting is that many sites that seem to require complex browser automation can actually be handled with simple direct requests once you understand what's happening behind the scenes. So with a demo e-commerce site that we have, this will load the items dynamically with a button. We can use a headless browser to click on it and so on. Or we can check that what the site does behind the scenes. We're opening DevTools here to see it. In this case, there's an internal point. Quite similar to a regular pagination call, it has a nice offset that we can surely change. We will probably need to mimic headers and other aspects of the browser like the referrer, but this can totally be done.
Okay, so I'm wondering if there's a similar case in how someone would handle a page setup with an infinite scroll. And or is this true?
Yeah, it is indeed a similar case. Usually the difference is what triggers the new content to appear. This video, the user is clicking on a button. In an infinite scroll case, the trigger is usually the user scrolling down to the bottom of the page, but the page's action will probably be similar. A call behind the scenes to retrieve new content and show it. The same techniques as above might apply. Use the tools to see how the target works and reproduce it in a programmatic way. Try to mimic the browser behavior.
Yeah, so when talking about optimizing for speed, parallel requests feel like the first option, but genuinely, I can't imagine that they're the only way. Why don't we jump into the next section and start focusing a bit more on resource optimization? Okay, so as I mentioned, we've seen some impressive improvements in both speed and efficiency in our previous section. But Ander, why don't you walk us through how this optimization process actually works?
Yeah, first, let's talk at a higher level and then we can jump into a specific example. Overall, what we see on many e-commerce pages, as an example, are things like images, styling, and other resources mainly meant for visual display that aren't necessarily important inputs for a scraping process. It's important to be selective about what we load so we can start cutting down the amount of data that and ultimately improve the speed and efficiency of our scraping.
Okay, that's helpful. But how do we actually visualize this for the audience?
Yeah, let's move on and I can walk us through a practical example. Let's look at a demo e-commerce page. So initially, it makes 50 requests and downloads 2.1 megabytes of data. This is just a regular request to an e-commerce site. Most of this isn't actually needed for scraping. It's images, styling, and other resources, as just mentioned. So this that we'll see now is a feature that Chrome DevTools has, which allows us to block certain URLs. In this case, all the ones with the .jpeg ending, and we can save 1.5 megabytes just blocking JPEGs. By being selective about what we load, what we don't, and so on, we can cut this down to 150 kilobytes approximately. So CSS, fonts, tracking, we don't need all of those. So granted, this page is blocking all of those and it looks unreadable, but machines and parsing libraries don't care about this. The content you actually want is present, the title, the product, the price. So now we move down to 44 requests. That's what it says there. But it actually, 26 of them are actually blocked, the ones you see red on the DevTools bar. We transfer 250 kilobytes of data, and the response time went down to 1.2 seconds. So not bad. Recap, we saved around 95% in bandwidth and almost 45% in time. But you know what? This could get even better. We can reduce this to just around 15Ks and a single request. When you're crawling thousands of pages, these savings compound dramatically. So using cache, we move from 2 megabytes in 2 seconds down to 15Ks and zero point 0.5 seconds. That's above 99% savings in bandwidth and 75% in time. Without these techniques, requesting, let's say, 12,000 similar pages per day, we will need around 25 gigabytes of data and around 20 hours of processing time. Now we are down to 200 megabytes of bandwidth in less than 2 hours.
Oh, wow. So, I mean, 19 to 2 hours, some pretty impressive savings, not only in terms of bandwidth, as you mentioned, but also processing time and I would imagine costs as well. So we've seen how caching can help us in a single instance, but what about larger operations? And again, this goes back to some of the earlier questions, but how do we scale this up, Ander?
Yeah, this is where things get interesting. When you're running multiple crawling instances across different machines, traditional caching isn't enough. Each instance could download the same resource repeatedly, wasting bandwidth and time. So the solution is distributed caching, creating a shared resource pool that all instances can access. Think of it as a central library that every crawler can use. While it requires more setup initially, the impact at scale is dramatic. The key is understanding that this is just about storage. It's about creating an efficient system for sharing and reusing resources across your entire crawling infrastructure. This is not something we will cover in depth today. It is a more complicated topic.
Okay, so I'm guessing a bit of a tease for maybe a future webinar, maybe. Okay, sounds good. Why don't we move on to the next topic? Okay, we have covered quite a bit of ground around optimization, but how do we put this all together? Ander, what would be your approach to building a robust crawling architecture?
Yeah, the key is having a systematic process, and we can summarize it in 3 steps. First, for a domain never crawled before, start from a seed URL. Usually, let's say it's the homepage. Then we extract all the categories available. This might be a simplification, granted, and several big sites will have a huge list, and you might need even to paginate extraction itself. Once all the categories are retrieved, extract the product URLs for each one. Again, in a long list, you might need to paginate. Visit each product page to extract the concrete data you're looking for: price, description, availability, images, and so on. Let me demonstrate the process with a quick and simplified demo example. So let's start, let's say, with a home page. This is a seed URL, and then we discover and extract the category pages and URLs. And finally, we access the products. It sounds simple, but the magic is in how you manage this information. As mentioned, this is simplified, and big e-commerce sites will have paginated categories. Big sites in general, not just e-commerce, will do the same. And for these long categories, as you see here, there are 13 pages. You need to iterate, but this is doable.
Yeah, but how would you keep track of all these URLs and know when to update them in the process?
Yeah, obviously that's crucial too. We recommend storing several pieces of information for each URL apart from the content itself. So last scroll date, canonical URL, response status, all of these will help us avoid duplicates, for example, and track changes effectively. For instance, if you discover a product URL that redirects to another URL, you can store both, but mark them as the same entity. And when it comes to updates, you need to be smart about it. Instead of recrawling everything, you start from the first page of each category. That's where new products typically appear. Of even better, order by recency if available. So some e-commerces do have this option. If you find new items, you keep going. If you hit items you've seen before, you can stop there.
And I guess the question I have is, what about products that might either disappear or change over time?
Yeah, when a product returns 404 not found, you shouldn't immediately delete it from your database. You should mark it as probably deleted, let's say, and check again in a few days. Sometimes it's just temporary unavailability for whatever reason. This is especially important in certain industries. Take real estate, for example. A disappearing listing often means it was sold. That's actually super valuable information. The time it was last available, the final price, these are important data points you can capture because of your storage strategy.
And what about, I guess the question is, how does this scale with larger sites?
Yeah, that's where the 3 step process really shines. From one homepage, we discover 11 pages, and that leads us to 188 products in the example above, so around 200 of them. We can crawl this in just 3 steps, also thanks to parallelism and concurrency we spoke before about. The same principle applies whether you're dealing with hundreds or millions of pages. It's just a matter of scale. Obviously, going bigger than a few hundred URLs will surely require a proper scheduling and queuing system. And on top of that, good practices like logging and separation of concerns are suggested. And here's also a final tip. Even with a robust system, I recommend doing a complete crawl periodically. It's just a safety net that helps catch any edge cases a regular update process might miss.
Okay. All right. Thank you. And okay, so now on to, I would imagine, one of the biggest challenges in web scraping. And or why do scrapers get blocked? And more importantly, how can the audience prevent it?
Yeah, anti-bot protection has evolved significantly. The biggest issue is usually IP detection. If a website sees too many requests from the same IP, it's an immediate red flag. But that's just the start. Sites also analyze behavior, how fast you browse, your request patterns, etc. They look at browser characteristics like screen size, fonts, time zone, whatever you can think of. If all of this don't align with what's expected from a real user, you can also get flagged. The key is understanding that these aren't isolated challenges. You might have perfect IP rotation, but if your browsing behavior looks automated, you'll still get blocked.
So how do we handle these? How does the audience address these challenges?
Yeah, we'll need to take several factors into account. First, you need proper IP management, typically using a mix of residential proxies and auto-rotating solutions, depending on the use case. But equally important is how you use those IPs. You need to maintain consistency and look human. Reusing cookies appropriately, if you're doing so, setting proper headers, ensuring your browser characteristics make sense for each IP, and many other things. If your IP is from New York, for example, but your time zone is set to Paris, that's a red flag, or at least an orange one. Some patches over headless browsers will change the user agent. This is super common for open software, but not the underlying platform or other parameters available in the browser. We need to assume that anti-bot systems will check everything in our connection and browser. As mentioned, IP, location, the browser itself, operative system, window size, screen size, many, many more. Consistency is key. More importantly, you need to think like the website you're trying to access. They're trying to protect against automated access. So every aspect of your request needs to look natural.
Yeah, I guess I have a quick question on IP strategy, and I think you mentioned a little bit about this before, but what's the difference between how sites treat a residential versus a data center IP?
Yeah, this is usually the first problem faced when trying to access a protected site. Data center IPs are good and fast until faced with a defensive system. The IPs are public, as is the owner. So from an IP, you can know who the owner is, and that's listed. That's available in the internet. So thus, we have to assume that the system we are facing will be able to check this data. We need to assume it, and they will know most of the time if the IP belongs to a hosting solution or a regular telecommunications company. Enter residential proxies or IPs. They will allow the connection to appear as a regular connection from a user in a home or a mobile IP address. And the owner will be a telco like AT&T or Vodafone. For the target system, this sounds much more credible than, say, Google data centers or AWS.
Oh, absolutely. Okay, why don't we move on to the next section? So we've covered all of these strategies. Now, how do we bring them all together effectively? What's the key to bringing this together and ultimately scaling successfully?
Yeah, the most important thing to understand is that scaling isn't just about going faster. It's about finding the right balance. Let me give you a practical example. When scaling up crawling operations, we start slow and gradually increase speed while monitoring success rate. If we see our success rate start to drop, we know we need to adjust before we trigger more aggressive blocking. The same applies to resource usage. Yes, we can use more proxies and servers to go faster, but there's always a sweet spot where the cost per successful request is optimized. Also, think about the infrastructure on your side, especially if you need headless browsers. Going from 0 to 1,000 requests in a second will require money to keep the machines warm.
And what about maintaining reliability at scale?
That's where queue management becomes crucial. Instead of running everything through a single pipeline, we recommend creating multiple queues with different priorities and speeds. New content might go through a fast queue, while updates use a slower, more conservative approach. This is, for example, the example we just mentioned from e-commerce. Updates can be periodic, like every week, say. You can schedule them low priority, but new content, you might want to get it fast. So different queue systems or priority systems will help. The key is also to continuously monitor and adjust. So protection systems are dynamic. Our approach needs to be dynamic too. The system needs to be ready to be scaled down just as quickly as it scales up.
Yeah, that makes sense. Are there typical bottlenecks that you might run into when it comes to scaling?
Yep. There are a few common ones that we can go over quickly. First, getting blocked will probably be the biggest challenge these days. Defensive systems are easier to integrate and more affordable than ever. Thus, the number of sites using them is going up. We saw above how relevant this part is, but still, most of the people still are hitting this. Another common one is using headless browsers. The slowness and high resource consumption. As we've seen earlier, there are ways to reduce the problem, but probably not eliminate it completely. We haven't covered this part, but there are some sites that might not be used with the tricks we saw above, like the scroll down, click, and see. So in those cases, maybe headless browsers are needed. That's hard to scale, as mentioned. We can help, we can make it faster, we can reduce consumption, but still, it will be hard. And more on the coding side, uh, updating parsers where targeting several or even hundreds of targets can get out of hand. We recommend separating the crawling and anti-bot handling parts from the data extraction and parsing itself. I guess that many people who's been in the industry for some time, they've seen that the parsers break down each week, month, or year, depending on how often the site changes the structure of the HTML. That's a super common problem. So that problem can be handled when it happens, but it will be super important to have a proper monitoring and alert system for us to know that something broke down and we need to change it. Lastly, proxy maintenance, rotation, and the consistency mentioned with the request content is not easy to achieve. There are many things involved here.
Okay, super interesting. So, wow, we've covered quite a bit of ground today. Why don't we take a step back and maybe have a quick summary of today's conversation? So, as I mentioned, we've covered a bit of ground. Why don't we maybe talk around the 7 sections that Ander covered in today's session? And Ander, can you maybe give us a quick review of those 7 strategies for web crawling?
Yeah, we've covered a lot of ground. Starting with parallel processing, we saw how to transform slow sequential crawls into efficient parallel operations. Then we tackled dynamic content, showing how to handle modern web applications effectively. Resource optimization and smart caching work together to dramatically reduce bandwidth and processing time and thus costs. Your crawling architecture provides the foundation for effective URL management, while your protection bypass strategies ensure reliable access to data. Finally, intelligent scaling brings it all together, helping you balance speed with reliability as you grow your operations. But as I also mentioned earlier, these strategies aren't meant to be used in isolation. They work best when implemented together as part of a comprehensive approach to web crawling.
Well, first of all, Ander, thank you. Thank you for the time and the insight. You're not quite off the hook yet. We've got some questions to jump into, but just before that, just to confirm for everybody, the demos that you showed and the resources that you made available in the presentation, will that be uh, made available to the attendees?
Yes, absolutely. You'll have access to all the demo sites we've shown today, along with the technical resources we've referenced. They're great starting points for implementing these strategies in your own system.
Okay, perfect. So as I mentioned, you are not quite off the hook just yet. We are going to move into some of the questions, and just for the audience, we are going to run through as many of these as we can, but we're also conscious of your time and the time that you've committed to us. For those that we are not able to address today, we can have our team reach out directly and contact you to be sure your question is answered. This is our world. We love hearing from you, and we love to hear from people on the topics like we discussed today. So please put your questions in the chat, and we'll jump in. And also bear with me as I try to navigate Q&A in live over Zoom. So let me do this, bear with me, and I'll get to one here. Okay, Ander, I've got one question here. It is, does the proxy affect crawling speed?
Well, short answer, yes, it does. It is a super relevant factor. And longer answer, the impact depends on factors such as the type, as we saw, residential data center, then rotating versus not rotating, and the response time they have, and the overall quality. High quality proxies, low latency, for example, low connection speed, this can maintain fast request speed, while slower, overloaded, or bad quality proxies will introduce delays. Then unstable proxies may frequently disconnect or fail to respond, causing retries and again delays in the crawling process. Then the quality itself will affect, because yes, you connect, yes, the request goes fast, but the IP quality is so bad that you get blocked every single time. That will also add delays and make it slower. So quality is obviously important. And additionally, and this is not super relevant, but in some cases this may affect, geographically distant proxies may increase latency due to longer networking routes.
Oh, that's interesting. Okay, bear with me. Let me see if I can find another. Okay, how do you identify the underlying data sources?
Yeah, I guess that this comes from the infinite scroll and click to pagina section. So in those cases, in general, the first step is to open DevTools and browse the site. Sounds simple. That usually will show where the data is coming from. Another useful feature that DevTools have, it wasn't shown in the video, but I usually do it a lot, is searching. Again, sounds simple, but bear with me. When some dynamic content is loaded and you don't know where it came from, it's not in the original HTML, for example, copy part of the content, literally copy it, go to the network tab on DevTools, Command F or Control F, paste and search. That will show the request containing the content. If you start there, you will probably see which URL it came from, and from there you can see how to mimic it. It was probably an internal call, XHR or whatever. And in those cases, you just need to get the URL, see how it was formed, where it came from, what user action triggered it. Check the headers, maybe it has some things that will only be added there. And then, as with the infinite scroll case, try to mimic it as best you can and try it. It might work.
Okay. All right. So I've got a couple here that feel like they may be related, so I'll just kind of put them into one question. So how have protection systems evolved? What new challenges are emerging? And finally, how do you stay ahead of protection updates? So again, I feel like those three are probably related.
Yeah, yeah, this could related, and I will talk a bit about history, so bear with me a few seconds, but we need to explain this. So we're going back in time, but back in the day, just IP rotation used to work, and this might sound old, but I'm talking about 10, 15 years ago. Uh, you added some random user agents, good IP rotation, and that was it. Basic HTTP clients could access almost any site just with that. Then active measures like CAPTCHAs or honeypots started appearing, so you needed to avoid those. Honeypots were, for example, invisible links that if you clicked and you went there, you were marked as a bot because no human would do it. So you needed to be careful with those. Plus also the blocking or at least limiting by IP origin, see data center proxy, see AWS, for example. Around 10 years ago, 2015 or so, things started to change big time. Uh, they started to check device and TLS fingerprinting, IP blacklisting, IP quality scoring. CAPTCHAs evolved a lot too, so and they were harder to solve. Uh, I actually had literally me myself not automatically had issues solving them, so I guess everyone had. And interactive and JavaScript challenges kept growing, which are the ones explained before, the ones about the screen size and the fonts, images, and so on. They will check everything. And we do this day in, day out. They render images in Canvas just to see if one browser renders is exactly the same as another one. There are things super crazy that go around that. And these past years, as everything in the tech industry, the wave is moving to AI, as everything else. So machine learning algorithms detect spikes and pinpoint them, for example. There are some interesting conferences in YouTube explaining exactly how they do it, and we've watched them and we've learned from them. They are able to compare several parts of the request separately, like country, origin, user agent, many, many others. So then they analyze in almost real time which feature in common the spike has, and they're able to ban or challenge only those with the, I don't know, maybe this country with this user agent is causing the spike, so they will challenge only those and leave the rest of the users unmolested, no ban, no challenges. So as for staying ahead, again, consistency is key. Good IP quality, trying not to look like a bot, maintaining the consistency we've been talking about in all the interactive checks and so on. There are many, many factors. We know it. But one thing is constant here, and it's change. If they keep evolving, we must do the same.
Yeah, absolutely. All right, I've got one more here. What headers are most important to manage?
Yeah, this relates to the above one, even if it doesn't look like it, because in the past, with the user agent, you were done. But short answer today, all of them. Long answer again. In the past, it used to be just user agent, maybe language header, but nowadays we need to assume that every single aspect of the request can be checked. The accept header that Chrome sends, for example, is completely different from the one that Firefox does. So if you send an accept header from Chrome with a user agent from Firefox, you can guess that the defensive system will be able to spot it. But it's worse because Chrome 131 sends different headers from Chrome 125 from 1 year ago, and you need to keep consistency among those two. And this applies to almost everything. We usually talk about header sets and not headers per se, since the user agent usually will require the rest to be in sync. So accept the languages and many, many others. On top of that, some requests like internals, XHR, or fetch requests will need also some extra headers that only those kind of requests will have. That being said, this is the pessimistic scenario. This might not be needed, but you can know for sure what the defensive system is checking now. But what might be worse, you might think it works now, but you don't know if they start checking it tomorrow or the day after or next week or next month. So just in case, we usually tell people, again, keep consistency, use the full header sets, and let's try to look like the regular browser you're using.
Okay, so conscious of time, Andrew, I think I've got one more for you. This might be a big one, so we'll dive into it. But it feels a little bit, well, it's definitely focused on IPs. How do you determine optimal IP rotation frequency?
Yeah, this will depend a lot in the target and the providers you are using. So when targeting, for example, e-commerce or real estate, as mentioned above, it's common to rotate per request. Since each request is independent and you want to run them in parallel, each request will have a different IP. That's not a problem. There are some providers that allow this with, it's usually called auto-rotating proxies. You send all the requests to the same endpoint, and internally the provider will automatically use one IP per request, and everything will work out of the box. For systems or providers that offer IPs or ports that maintain the same IP for a few minutes, say 10 minutes or forever, you have to be careful with the frequency of each one of them. Sending tens or hundreds of requests from the same IP in just a second can get the IP ban. If instead you send one request per IP or port, then after a few seconds you do the same, each IP will be seen just every few seconds. That's a bit better. That resembles a human behavior, just a person browsing. And the last case that comes to my mind is session management. This is completely different. In this case, the idea is to maintain the same IP and browser config. So while using the same cookies or session, this is exactly what your regular Chrome would do. Also taking into account that hundreds of requests per second with the same cookies, they won't look real. In those cases, you can do as with the IP port above. Keep a pool of IPs and session pairs and use them every few seconds or even minutes if you can afford it. For this, you need a provider that can get you the same IP for at least a few minutes, 10 minutes, 15 minutes, whatever you need. Anyway, for these two last cases, you can always keep track of the success rate. If a concrete IP or port or session drops, remove it from the list or the pool and get a new one.
Okay, I know we're close to time. We've got some questions in here that are really good around bypass captchas as well as parallel processing over concurrency. We've got a couple on integrating LLMs into the broader context of some of the conversations we were having, but unfortunately we are running out of time. As I mentioned earlier, we will circle back on those. Thank you for submitting them, and genuinely thank you for joining us today. Thank you to Ander for being our speaker and taking the Q&A, and more importantly, thanks for everyone for joining Zenrows in this webinar. We appreciate the terrific questions and look forward to seeing you soon. Keep an eye out for an email from us for a recording of today's session and a link to the resources that Ander mentioned earlier. We will also be sending an ebook on the topic that we will share in the coming days to continue to sort of evolve on this thread. So again, eager to keep the conversation going. Thank you for joining us and looking forward to seeing you next time. All the best. Thank you. Thank you.